Hello, welcome back to Topic 5, Bonding. This is Section 5.3, Ionic Bonding, and our aim for today is to describe the formation and characteristics of ionic bonds. So what is ionic bonding? An ion is a charged particle. Remember, the difference between an ion and an atom is an atom has a neutral charge, no charge, and an ion has a charge. How does it get its charge? By gaining or losing electrons. So they form when atoms gain or lose electrons. Ionic bonds form when oppositely charged ions bond together. So you have a positive ion and a negative ion bonding together, and that gives us an ionic bond. For an example, a sodium ion, which is Na+1, and a chlorine ion, chlorine -1, will form an ionic bond, since one is positive and the other is negative. This usually occurs between metals and nonmetals. So ion formation in metals. Ions usually form with noble gas electron configurations, which means a full valence shell. So the two substances that are combining for an ionic bond want to find that full shell and come to 8 in their full valence shell. Atoms want to gain or lose electrons to look like noble gases with a full valence shell. Metals lose electrons to acquire the more stable octet arrangement of a noble gas. An octet, as you remember, is 8 electrons in that outer shell. Atomic radius decreases when it loses a shell. So if you lose an electron shell, it gets smaller. So this is just showing how if you have a sodium ion and it loses its valence electron, which is only one valence electron, it now only has 2 shells instead of 3. So your sodium ion is going to have a smaller radius. When your chlorine atom with 7 valence electrons gains an electron, okay, that's going to complete its valence shell. And these two together attract each other, since one's positively charged and one's negatively charged, and they form an ionic bond of sodium chloride. Okay, ion formation in nonmetals. Nonmetals gain electrons to acquire a full valence shell. They tend to have 5, 6, and 7 valence electrons, so they want to gain electrons to fill up their outer shell to achieve noble gas electron configuration. So atomic radius increases when you add electrons to the valence shell. When metals react, they lose electrons, which makes them positive, because when you lose a negative, you get positive, which gives them a smaller radius, and they acquire the electron configuration of a noble gas. When nonmetals react, they gain electrons, which gives them a more negative charge. They're gaining electrons which are negative. This gives them a larger radius, and they acquire the electron configuration of a noble gas as well. So your ions help each other out in an ionic bond to gain our full octet of electrons. Electronegativity. On table S, this shows the electronegativity of the different elements, and this shows the atom's attraction for another atom's electron. Okay, so electronegativity is how attracted the protons in the nucleus are to another atom's electrons. When the electronegativity is closest to 4.0, this is a very strong attraction, and when it's further away from 4.0, it's a really weak attraction. The electronegativity difference we calculate by subtracting the electronegativity of our two ions. So we subtract to find the difference between electronegativities of the two different atoms, and this difference determines what type of bond. So right now we're talking about ionic bonding, but this same subtraction of electronegativity, our electronegativity difference, will tell us when we go forward what type of covalent bond we would have as well. So when we calculate the electronegativity difference, if the difference is greater than 1.7, we have an ionic bond. Okay? So for example, let's turn to table S in our periodic table. Okay, so if you don't have your periodic table, let's get it out now. So we're going to look up the electronegativities of sodium and chlorine for NaCl, sodium chloride, and we're going to look up the electronegativity for hydrogen and oxygen. Okay, so sodium has an electronegativity from our table S on page 10 of 0.9, and chlorine has an electronegativity of 3.2. And if you subtract 3.2 and 0.9, we get an electronegativity of 2.3. This is greater than 1.7. Oops. This is greater than 1.7, so therefore we'd have an ionic bond. Now for hydrogen, the electronegativity is 2.2, and oxygen's electronegativity is 3.4. So our electronegativity here would be 1.2. This is less than 1.7, so this would not form an ionic bond. This is a covalent bond, which we're going to talk about in our next section. So the electronegativity difference of 1.7 or greater gives us a ionic bond. So if we have greater than 1.7, it's ionic bond. So let's look at now magnesium and oxygen. Okay, same thing. Look up the electronegativity. Okay, magnesium's is 1.3. And oxygen is 3.4. So you can see this is a large difference. So this gives us a difference of 2.1. So this also would form an ionic bond. Also keep in mind magnesium is a metal and oxygen is a nonmetal. And this is another way we could tell that this is ionic. An ionic bond forms between a metal and a nonmetal. Okay? With ionic bonding, there's a transfer of electrons. So in this case, our magnesium is transferring its 2 valence electrons to oxygen. So oxygen stole magnesium's electrons. Since magnesium has 2 valence electrons and oxygen has 6, if magnesium gives up its 2 and gives them to oxygen, now oxygen has a complete outer shell and so does magnesium. So this is how ionic bonding works. They help each other out by the metals passing off their electrons to the nonmetals to complete their shell, and magnesium loses its outer shell, which leaves it with a complete shell as well, and everybody's happy. Okay, so this is the table we're using. We're using electronegativity right here. So let's do some more practice. Okay, you could pause here and fill in this table and then verify your answers with mine. That would be a good way to do this. So find the electronegativity for each element, then subtract to get the difference. And if it's greater than 1.7, you have an ionic bond. Okay? If it's less than 1.7, you do not have an ionic bond. Then you would have a covalent bond for the most part, but we'll get to that in the future. Okay, so I'm going to complete this table if you have now paused and come back. Okay, so calcium has an electronegativity of 1.0. Fluorine is 4.0. So our difference is 3.0, and we have an ionic bond. Okay, lithium has an electronegativity of 1.0. Bromine is 3.0. So the difference is 2.0, and this again would be ionic. Okay, if it's greater than 1.7, it's ionic. Potassium, 0.8. Oxygen, 3.4. Difference is 2.6. So ionic. Oops, 2.6. This is ionic. That's a 2.6. My pen is not cooperating. Okay, beryllium is 1.6. Sulfur is 2.6. So our difference here is just 1. So in this case, we do not have an ionic bond. This is not ionic. Okay, this would actually be covalent, which is our next topic. So just calculating the electronegativity difference can give you your type of bond. So let's find which bond is least ionic in character. So we're going to find the electronegativity differences for each of these pair of elements. And the closer it is to 4.0, the more ionic. The lower that number in difference in electronegativity, the less ionic. Okay, so we're looking for the smallest difference to find the least ionic in character. Okay, so hydrogen, looking at table S, has an electronegativity of 2.2. So I'm going to fill in 2.2. Fluorine is 4.0. So our difference here, our electronegativity difference, is 1.8. Hydrogen again is 2.2. Chlorine is 3.2. So our electronegativity difference is 1.0. 2.2 for hydrogen. Iodine is 2.7. So our difference here is 0.5 and 2.2 for hydrogen again. Oxygen is 3.4. So here our difference is 1.2. So the least ionic here would be the smallest difference, which would be choice 3. Which compounds contain the greatest degree of ionic character? So now we're looking for the largest difference in electronegativity. Okay, that would make it more ionic. Okay, so sodium has electronegativity of 0.9 and fluorine is 4.0. So our electronegativity difference here is 3.1. Magnesium is 1.3. Fluorine again is 4.0. So our difference here is 2.7. Aluminum is 1.6. Fluorine, still 4.0. Our difference here is 2.4. Silicon, electronegativity is 1.9. Fluorine is 4.0. Our electronegativity is 2.1. So you can see all of these have ionic bonds, so they're all greater than 1.7, but the most ionic is the biggest difference. These have the biggest difference, which makes them the most attracted to each other, and the strongest bond, which would be the 3.1 for sodium fluoride. Which element forms an ionic bond with fluorine? So an ionic bond, we're looking for a bond between metal and nonmetal. So fluorine is a nonmetal. So we're looking for a metal to then be bonded to fluorine. So it can't be bonded to itself. That would not be ionic. Carbon is also a nonmetal. Potassium is a metal. And oxygen is a nonmetal. So our ionic bond here would be potassium. The elements lithium and fluorine combine to form an ionic compound. The electron configurations within the compound are the same as the electron configurations of atoms of group. So lithium and fluorine combine to form an ionic compound. The electron configurations in the compound are the same as the electron configuration of atoms of group. Okay, so lithium, the ion. Okay, look at your periodic table, and lithium has a valence electron with 1 and gives it a charge of +1. Fluorine has 7 valence electrons, which gives it a -1 charge. So when these two combine, right, lithium's valence electron, it's 1 valence here, where fluorine has 7. So when this is transferred to fluorine, fluorine now will have a full 8 with a minus charge. Lithium now goes down to it'll have just 2 in its outer shell, right? So this one, it lost its valence electron. So now the electron configuration of the compound would be the same as group 18. They both have a complete shell like a noble gas. Which ion has the electron configuration of a noble gas? So we know a noble gas has 8 valence electrons. So let's look at copper. Copper has 1 valence electron. So +2 means it is losing 2. Okay, so its ground state configuration is 2, 8, 18, 1. If it loses 2, it's losing this one and 1 from this third shell. So its ion electron configuration is 2, 8, 17. So this would not be the same as a noble gas. Iron has 2 valence electrons. Its configuration is 2, 8, 14, 2. If it's plus 2 charge, it's losing these 2, but this gives it 14 in its valence shell, which would also not be the same as a noble gas. Noble gases have 8 in their valence shell. Calcium, its electron configuration is 2, 8, 8, 2. It has a plus 2 charge, so that means it is losing these 2 outer shells, those 2 outer electrons, excuse me, which gives it a configuration of 2, 8, 8. So if you look at argon on the periodic table, argon's electron configuration is 2, 8, 8. So this would in fact be the same configuration as argon. So calcium as an ion with a plus 2 charge has the same electron configuration as argon. And that completes our notes for today. See you next time.